Hello friends, welcome to this video on inverse Laplace transform. Inverse Laplace transform of a given function can be estimated using different methods. We already saw about the method of partial fraction in the last video. This video will help you to find the inverse Laplace transform of any given function using the method of convolution. Come on, let's get started with the method of convolution and how to apply it to find inverse Laplace of a given function. Convolution of two functions. Say suppose f of t and g of t are your given functions. Then the convolution of f of t and g of t is defined as f of t convolution. This is going to be the symbol we are going to use asterisk for the representation of convolution. So f of t star g of t is defined as integral from 0 to t f of u g of t minus u into du. F of t star g of t is integral from 0 to t f of u g of t minus u du. Now, what is meant by convolution theorem? If we have f of t and g of t to be functions for which t is greater than or equal to 0, then the convolution theorem says Laplace of f of t convolution g of t can be split into product of Laplace of f of t and Laplace of g of t. Notice within the bracket it is remaining as convolution. When this convolution gets separated, it gets separated as product. So this simplifies the process to a greater extent. We can have the corollary of the convolution theorem as Laplace inverse of f of s product g of s is Laplace inverse of f of s convolution Laplace inverse of g of s. So when you take Laplace inverse to product of two function, they can become split into Laplace inverse of convolution of these two functions. Come on, we will now apply convolution theorem to solve Laplace inverse problems. Let us find the Laplace inverse of s by s square plus a square the whole square using convolution theorem. If this word convolution theorem using is not given in the exam, then we can solve the problem by any method. But if the process has been specified, we will have to strictly stick on to the given or the required process and hence evaluate it by the process. Now, this function Laplace inverse of s by s square plus a square the whole square can be written as Laplace inverse of s divided by, here you have a whole square, let me split it as s square plus a square product 1 divided by the second factor as s square plus a square. Now, what do we know from the convolution theorem's corollary? We know that Laplace inverse of f of s product g of s can be written as Laplace inverse of f of s convolution Laplace inverse of g of s. So the product over here gets split as two quantities with convolution in between, like Laplace inverse of s square plus a square convolution Laplace inverse of 1 by s square plus a square. Now we know the Laplace inverse for the given quantity. This is s on the numerator, so the function has to be cos. You have a in the constant part, so this gives me as cos at. Convolution. How about the second quantity? Here you have constant in the numerator and you have a square as the constant in the denominator. Hence, to apply the formula, what you require is a in the numerator. So balance it with a by multiplying and dividing it. So this gives me 1 by a times, now a by s square plus a square's Laplace inverse makes it as sin a t. So I have Laplace inverse of s by s square plus a square the whole square to be equal to cos a t convolution 1 by a sin a t. So this 1 by a being a constant can be taken outside to have it as cos at convolution sin at. Now let us refer back to the definition of the convolution and apply the same to this quantity cos at star sin at. Now we know that f of t convolution g of t is integral from 0 to t f of u g of t minus u du. What we have is going to be cos of at convolution sine of at, and we have a constant which is 1 by a outside. So we will just consider the convolution of these two alone. What we have in place of f of t is cos at. What we have in place of g of t is sin at. So this can be rewritten as 1 by a integral from 0 to t f of t to be replaced with u. So cos at will become cos a u into g of t minus u. This is g of t. Wherever you have t, replace this t with t minus u. So we will have sine of a times t minus u. So into du. This will give us integral from 0 to t cos a u sine of at minus au into du. Now this is of the format cos a sin b. We will have to be very careful to handle the product of the quantity, in which case we will have to be very confident on the trigonometric formulas which we have learnt in our lower grades. We will try to recollect them fast and quick. Now what we have over here is cos A sin B. Let us identify this as this is to be cos A and sin B. Now what we know about cos A sin B? It is sin A plus B minus sin A minus B divided by 2. So we have this as 1 by A integral from 0 to t sin of A plus B au plus at minus au. So this is a plus b minus sine of a minus b au minus at plus au times divided by 2. So let me take this 2 outside, and this has to be integrated with respect to du. Now in the first term, positive au, negative au cancels off, leaving you with 1 by 2a integral from 0 to t sine of what is left out is at into du. Let me separate this into second term minus 1 by 2a integral from 0 to t. Now you have au here, so it is sine of 2au minus at into du. Now we have two integrations which has to be evaluated for. The first integration is 1 by 2a integral from 0 to t sine of at into du. Now you can see the integration is carried out with respect to which variable? U. But over here, this quantity doesn't contain a u, which means this sine at is treated like a constant. So this constant can be brought outside the integration, leaving you with just du for integration. We know that du on integration gives you u between the limits 0 to t. So this gives me 1 by 2a sine at, and this upper limit minus lower limit will give me t. But by any chance don't multiply it with this t. So we can just bring it to the forward and write it as 1 by 2a t sine at. So this completes the first part. Now moving to the second part. What we have in the second part? Sine 2au minus at into du. So we have minus 1 by 2a integral from 0 to t sine of 2au minus at with respect to du. Now, this sign contains an u inside and hence becomes a function of the integrable u. Hence, on integration, we have this to be equal to sine theta on integration gives you minus cos 2au minus at divided by the angle of integration with respect to u. What is going to be the constant appearing here along with u? So it is going to be divided by 2a. This has to be applied between the limits 0 to t. So I have this to be equal to minus into minus. So this makes it to be equal to plus over here with, now apply the upper limit for it. So minus of minus will become plus 1 divided by 2a. 2 2s are, this will become 1 more 2a over here. And when you apply u to be equal to t, this gives me cos 2at minus at for my numerator, sorry, the upper limit. And how about the lower limit? Minus sine of cos of, this u will now take the value 0. So the first term will become 0 minus 80. So this is what we have. Now this gives us cos 2at minus 80 makes it as cos 80 minus, this is cos of minus 80. What do we know about cos of minus theta? Cos of minus theta is the same as cos theta. So again, this will be equal to cos at. Now, this quantity, which is going to be cos at, cancels off with this minus cos at, leaving you this term to be equal to 0. Hence, we just have the first part of the integration to exist and the second part vanishes. Therefore, by the theorem of convolution, we have found out the inverse Laplace of the function 1 s divided by s square plus a square the whole square as 1 divided by 2a into t sine a t. So this will be our final answer. We will try to apply convolution theorem to one more problem. Problem number 2. Find Laplace inverse of 1 divided by s square plus 4 the whole square using convolution theorem. So, using convolution they have given. Therefore, we stick on to the theorem to apply it. Now, how I can split this Laplace inverse of 1 by s square plus 4 the whole square as? I can rewrite this as 1 divided by s square plus 4 product 1 divided by s square plus 4. Whenever I have it as product, by the corollary of convolution theorem, I can split it into two terms, s square plus 4, but this multiplication on splitting becomes convolution of 1 by s square plus 4. Now this gives me Laplace inverse of 1 by s square plus 4 requires a 2 in the numerator because this is s square plus 2 square. So balance it by a 2 by multiplying and dividing. Similarly, here also you require 1 by 2 and 1 by 2. So this totally makes it as 1 by 4. So the quantity, the first one which we have is, since it is a constant, this is going to be sine 2t convolution with, again, this is going to be sine 2t. So I have 1 by 4 times sine 2t convolution sine 2t. So now let us identify this with the formula for convolution. What do we know about the formula of convolution? I can just rewrite this to be equal to 1 by 4 integral from 0 to t f of u. So this is my f of t and this is my g of t. So I want f of t to be replaced by u. So this becomes sine 2u and this second term becomes sine 2 times of t minus u du. So now we have it of the format sin A, sin B. Now identify the given structure sin 2u, sin 2t minus 2u du with the trigonometric identity. What is the trigonometric identity? Sin A, sin B. What is going to be sin A, sin B? Cos A minus B minus cos A plus B divided by 2. So this becomes integral from 0 to t cos A minus B. So 2u minus 2t minus of minus will become plus 2u minus cos A plus B. So 2u plus 2t minus 2u and the whole thing is divided by 2. So let me take this 2 outside. Entire thing is integrated with respect to du. So this gives me 1 by 4 2s are 8, 0 to t. What happens over here? The first term gives me 2u and 2u. So that makes it as 4u minus 2t and second term is going to be 2u cancels off cos of 2t into du. Now when I integrate cos of 4u minus 2t du gives me sine of 4u minus 2t divided by the constant value over here with u is 4. So it will be divided by 4. When it comes to the second term, it is entirely t and no u. So this cos 2t will be retained as such with a u which will be now applied between the limits of 0 to t. Now let us apply the limit for u as t and 0. The upper limit minus lower limit. So what we will be having is 1 by 8 sine 2t by 4. Second term will be t cos 2t. Third term will be sine 2t divided by 4. Okay. So now this sine 2t and this sine 2t can be combined to give you 2 sine 2t by 4 minus t cos 2t. Now this can further be simplified to 1 by 8 times sine 2t by 2 minus t cos 2t. Now let us complete the session with one more problem. Find Laplace inverse of s square divided by s square plus a square into s square plus b square using convolution theorem. Now let me split this quantity as Laplace inverse of s by s square plus a square product s by s square plus b square. Because I have 2s, I can split it equally for both of them. Then by convolution, this product over here becomes convolution. So this gives me whole thing convolution Laplace inverse of s by s square plus b square. Now since we have s in the numerator, the Laplace inverse is nothing but this is going to be cos A t convolution cos B t. Now apply the convolution theorem to it. Integral from 0 to t cos A u. This is going to be cos B times t minus u du. Hence we have it as 0 to t cos A u cos, this is going to be bt minus bu du. Now this is of the format cos A, cos B. So the format is nothing but cos of A plus B. So it is AU plus BT minus bu and plus cos a minus b. So it is au minus bt, minus of minus will become plus bu divided by 2. So this divided by 2 comes outside with integral from 0 to t. The entire quantity has to be integrated with respect to du. So let me make this as integral from 0 to t. On simplification, it gives me cos of, which is going to be unique over here with respect to the function, is going to be u. So let me correct u separately and the t term separately. Bt is a constant and we have a minus b times of u. That is au minus bu, a minus b times of u. In a similar fashion, over here also collect your u term separately. So it is cos of a plus b times of u minus bt. Now this has to be integrated with respect to the component du. On integration, cos theta gives me sin bt plus a minus b times of u. With respect to integration, the constant of u is going to be a minus b. So it becomes a minus b in the denominator. Second term, cos on integration gives you sin of a plus b times of u minus bt and then divided by coefficient of u is a plus b, that gets divided. Now apply the limit between 0 to t. So when we apply, we have this to be equal to sin of bt plus a minus b times of t. So upper limit divided by a minus b plus sin of a plus b times of t minus bt divided by a plus b. So this is my upper limit. Now coming to the lower limit. When you put 0 over here, this term vanishes, leaving you with sin bt divided by a minus b. How about the second term? Minus sin, this will become 0. Sin of minus bt will become minus sin bt. Sin, that is sin of minus theta is minus sin theta. Already we have a minus sign here. So this becomes plus bt divided by a plus b. Now 4 terms are there totally. Let us simplify this furthermore to get this as 1 by 2 sin at divided by a minus b. Second term is sin at divided by a plus b. Third term is sin bt divided by a minus b. And the last term is sin bt divided by a plus b. You can leave it as such, or you can go one more step ahead to simplify this as a plus b into a minus b makes it as a square. And so we will make it as a square minus b square. So next step will make it as, so you will have to multiply with a minus b is there, a plus b you will have to multiply. Over here a plus b is there, a minus b you will have to multiply and adjust. So you will have 2a sin at minus 2b sin bt. Now on adjusting, this 2 over here can be cancelled off with over this, and now this leaves you with a sin at minus b sin bt divided by a square minus b square. Hence this completes the problem on convolution.